Okay, so good morning, everyone, and thank you for being here. And today we are very excited to have Andrés Monsalve. He's a PhD student at the University of Texas, El Paso, and he will be our speaker today. And he will be discussing fair AI models benchmarks. And the recommended lecture for this session was on the measure of intelligence by Cholet in 2019. So welcome, Andres, and the floor is all yours.
Thank you, Leila, and good morning to everyone. I'm happy to be here. This presentation is intended to last around 30 minutes or a little less. The article we're talking about was written by François Cholet in 2019, and it discusses like a fairness in AI model evaluations, right? When we evaluate like an artificial intelligence model, mm, to do that, we need first to define what intelligence is. There are multiple like approaches to the definition. These two are author, authors in 2007 like summarize what psychology uh, categorizes as intelligence. And but there are two different divergent versions of intelligence. Like one is intelligence as a collection of task specific skills, and the other one is the intelligence as a general learning ability. This collection of task specific skills is what symbolic AI is about. Like symbolic AI is this AI paradigm on which rules are hard coded into the system, or and on the other hand, connectionism that is relates more to the general learning ability is the paradigm where rules are implicitly discovered by the system on the connections it makes. Like this is the case of deep learning, what AI is pretty much about right now. On the task specific skills, I'm sure you can recall that uh, at the beginning of the field of AI, the goals were pretty much like, let's develop a system that play chess that better than anyone else, or that play these little different games that than world champions. That were milestones achieved like in the 70s, like recently for other more complicated games. But that's still like a machine that performs well on a task, but without like this ability to generalize, right? So they also talk in this article about what AI evaluation is about, and this narrow evaluation or skill-based evaluation. There are usually like four methods to do this. One is with human review, that is rarely used because, well, it's expensive, it's impossible to automate, and it's kind of subjective, right? There's another approach that is the white box analysis. This is the best to fully describe environments, like where all the inputs can be explicitly enumerated. This becomes more or less like an optimality problem or proof. There exists the peer confrontation. That's the better system when you try to create models or systems that play player versus player games or things like that. And well, the benchmarks that we mostly use, where we train and then validate for a set of known responses or true true responses, right? So we want to evaluate the right thing, and we want to be fair with these systems we are creating. And I'm sure you're pretty familiar with some of these names on the top left: the Turing test, the Robot College Student test. These were like milestones, like settled long time ago. Like if a machine is intelligent, as we know it, like it should be able to convince people that it is not a machine, like in the Turing test, or to be able to graduate from college and take classes, or to be able to get to a random kitchen and serve a cup of coffee uh, autonomously. But um, I like this image in the right that says that when measure becomes a target, it ceases to be a good measure. Like ChatGPT right now can achieve most of this task, like can pass college level tests without attending the classes. And well, evaluating skill alone does not move us forward, but the abilities are an abstract construct, and it's hard to measure, right? Um, when I say that this does not move us forward, like is because optimizing for a single purpose performance is valid if one's measure of success can capture exactly one six. For example, if one ends goal is to play chess, well, it will do right like the way it's being actually measured. But from the moment the objective is settled, the process of developing a solution will be prone to taking shortcuts, right? That's the case on what happened on Kaggle competitions, coding competitions, that usually these responses or winner models are overfitted and not really deployable or in real world applications. So there's a thing that is called generalization. Generalization, like, is the ability to handle situations or tasks that are differ from previously encountered situations, right? But these previously encountered situations has like a little uh, shady thing underlying, because well, there exists the system-centric generalization, that is, well, the system hasn't trained over this data, so we can use it to test. But systems are developed by developers, right? And the developer can hard code like solutions inside like the system nature. So there exists another type of generalization, that is the developer aware, that takes into account that the developer does not know either like these situations beforehand. The generalization is also an spectrum that we could classify into four, maybe five categories. The fifth could be universality. But well, that's like the generalization beyond the domain of human knowledge, and well, it's not practical to work on that level. But on these four levels of generalization, we are biological forms of intelligence. Humans and possibly other species are the only one, the only example I have like of extreme generalization. But in the broad generalization category, it can be argued that let's say self-driving cars, or I don't know, domestic robots can be this category. Like, it is open to discussion, I believe. On local generalization, are the models like we mostly develop, the classification or the machine learning models. And there exists an absence of generalization that can be seen when no certainty is present. Like, a sorting algorithm cannot be said to generalize over all natural numbers, because well, there is no uncertainty associated to the natural numbers, right? Well, after defining like this generalization, most of us can agree that um, the humans have like this intelligence that is more or less understood, or better understood than other types of intelligence in nature. um the this generalization ability or general intelligence is called G factor by the author. That it, well, refers to the cognitive abilities at different degrees, but that are related across tasks. Like, this generalization ability works on different tasks and can adapt and learn from each interaction. Human intelligence is not universal and is biased for human relevant tasks. What I mean by bias, or what did the other mean by bias, is like we are very good for tasks that involve 2D or 3D, like understanding, but beyond that dimensionality, like our performance decrease. That's kind of a human bias we have. Um, So yeah, an intelligence that we aim to measure has to be like well defined and to the scope of applications, right? So to the author also proposed to no longer neglect like the insights coming from a community that has developed human intelligence test for decades, that as is psychometrics, right? So they propose like an like for AI to include some principles of psychometrics that can inform the evaluation process for the AI models. These principles are like measuring broad generalization and skill acquisition efficiency better than skills, right? To use a batteries of tasks rather than a single task. Psychometrics usually like find the use batteries of tasks and the probabilistic measure out of them, like averages or weighted averages out of the performance of each of these tasks to measure like the intelligence of what they aim to measure. And well, they also include explicit standards regarding reproducibility, validity, standardization, and freedom from biases. The other refers also to something known as knowledge priors. Like if we aim to compare the intelligence of two systems, mm, we have to make sure that those two came more or less from a similar background. Like one has no advantage over the other in the beginning. So that in the context of the proposed framework here means like for object nets and elementary physics, this refers to the principles of cohesion, like the objects move as a continuous connected whole. The persistence, like the objects cannot disappear or appear suddenly. Contact, like the objects can interact with each other, like by touching. The other prior could be agentness and goal directedness, like a system should be able to either like recognize an inanimated object and an object that has could have some intention, right, or some goal. Could the system should be able to understand or have an abstract number representation, right? To sort, to subtract, to add, to understand magnitudes and compare them, and some elementary geometry and topology notions like orientation, in and out relationship, size, among others. Those are like the priors that our system in this framework should have like to start from. Well, doing a synthesis that all we talk right now, like first, intelligence lies in broad abilities and is marked by flexibility and adaptability rather than skill itself. A measure of intelligence should imperatively control for experience and priors, and should seek to quantify the generalization strength. Since unlimited priors or experience can produce systems with little to no generalization power but very high skills, right? Like doing like this cheating can be said. That's why the author proposed to control for this for prior and experience, right? Like to normalize by this. Like the more information you inject into the system, well, that will take points out of your system. And intelligence and its measure are inherently tied to a scope of application. Well, so as such, general AI should be benchmarked against human intelligence and should be founded on a similar set of knowledge priors, right? It's not like human intelligence is the best intelligence, um, but we cannot fully understand like camouflage in octopus and sonar or radar in dolphins, things like that. So that's a benchmark, the best benchmark we have. So now, for the position of the problem, here we have a sketch of the interactions within our intelligence system, right? We implicitly consider the existence of a universal Turing machine that can run any program, including the skills program, as well as the tasks. And we also assume the existence of a situation space and response space. These spaces defines like the set of binary strings like acceptable as inputs and outputs. Now let's talk about a little each element. The task in this framework is composed by a state, a task state that is a binary string, a situation generation function that may be stochastic, and a scoring function that returns a scalar, that is this score, and a binary, that is the feedback based on the situation, the response, and the task state. And the task update function that update the task state based on the response. Our intelligence system is composed of three elements. One is the intelligence system state, that is a binary string, and a self-update function which mutates the system state based on the situation, the response, the feedback of the task, and the previous state, and a skill program generator. It creates a skill program that basically is a function that maps an input situation to a valid response. The interaction like between these elements happens in two phases. One is the training phase and the evaluation phase, as we are used to. The training phase, like for the intelligence system, consists on generating this skill program that will generalize to future evaluation situations. And the evaluation phase uh, aims to assess the capability of this skill program to handle new situations. The training phase has multiple stages that very quickly going over them are like first the intelligence system generate a training situation. um we generate a training situation. The intelligence system generates a skill program without knowing like the current situation. The skill program outputs a response to the situation. The task scoring function assigns a score and sends feedback, and the intelligence system updates the internal state and generates a new skill program. That's the training phase, like creating this skill program. And the evaluation phase is superficially similar to the training, but the difference that the task in the evaluation phase starts from the test best initial state found at training. And it involves um, a single skill program. The skill program is not uh, updated anymore during evaluation. So basically, interaction is between the skill program and the tasks, and no longer involve the intelligence system. I would like to introduce some definitions used ahead for those of us that are not so familiar like with this mathematics. One of one of them is the algorithmic complexity that is noted here as h of s, and is the shortest description of the string in a fixed universal language, or the length of the shortest algorithm that describes my element completely. An example of this is like if you have a sequence of 1, 0, 1, 0 up to 100, the shortest program that describes that element could be 1 0 times 100. Like way shortest, that's the algorithm complexity of my element S, right? Like a very basic example. We also define the relative algorithmic complexity, that is like the length of the shortest program that taking S2 as input creates S1, but S2 that is not included on that length. And then the generalization difficulty from task 1 to task 2 is the ratio between the algorithmic complexity for the solution of task 2 of the algorithmic complexity of the solution of task 2, given that we start from the solution of task 1. With this in mind, we can now start quantifying the generalization difficulty, experience, and priors using algorithmic information theory. First, we consider like a task T, the solution for a certain skill. Theta is the skill and T is our task. Is the shortest of all possible solutions of T with a skill threshold theta. This theta is user defined because every skill program will perform one way or the other with a task, right? Interact with a task, and we set a performance level like to say, okay, after this performance, that can be considered a solution. And well, this element is the shortest all optimal training time solution given a curriculum. The author defines the developer aware generalization difficulty as this. That is the fraction of the algorithmic complexity of the solution that is explained by the training time solution and the initial state of the system. In other words, is the length of the shortest program that taking as input the initial system and the training solution over a curriculum of situations produces a skill program that performs at a skill level of at least data during evaluation. This is normalized by the length of that skill program. Is we're noticing that is this quantity ranges between 0 and 1. And also notice that a system that starts with the ability to perform well on evaluation situations for a task, sorry. So it starts with very high skill to perform on certain tasks. That will have a very low developer-aware generalization difficulty because the program that comes from here to here will be very short compared to the program that describes this element by itself. Now, they define the priors of an intelligent system. And the priors can be interpreted as a measure of how close from a sufficient or optimal solution the system starts. This is like the amount of relevant information embedded in the initial system. Notice that is not the amount of information, but the amount of relevant information, like the one that approach us to the solution, right? So the prior is also formally like the fraction of the algorithmic complexity of the shortest solution of T of skill threshold theta that is explained by the initial system at the start of the training phase. It no longer involves the results from the training as the developer-aware generalization. And then we can define experience at step T uh, as a measure of the amount of relevant information received by the system about the task over the course of a curriculum. Note that this is the difference between the algorithmic complexity of a solution at certain intelligent system state at time t minus the same element given that we got new data. What is this new data? Is the result from the interaction between the skill program and the task that has as outputs or inputs the situation, the response, and the feedback, right? When we want to have the experience over the whole curriculum, that is this set of interactions, um, we sum over the experience calculated for each step or iteration, normalized by the complexity of the solution. All these values ranges between 0 and 1. And then, without further ado, we arrive to what the other call like the measure of intelligence. over a certain scope, right? Let's talk about each one element of this formula. So the intelligence is associated to a certain task skill threshold, to a certain applicability or scope of abilities, and it's an average, right? It's an average for over each task belonging to this scope of applications of the skill shown during this task, but it's a subjective skill value because it is weighted. Like you can assign importances to different tasks, um, times the sum for each element of the curriculum or over each like situation response step of the probability that given curriculum occur times the developer aware generalization difficulty over the prior plus experience. Like you're dividing by the total problem info that your system was exposed to. Or in plain English, this whole equation, like intelligence is the rate at which a learner turns its experience and priors into new skills at valuable tasks that involve uncertainty and adaptation. Now, some possible additions to this definition, like for the previous definition, the authors solely like consider information efficiency of intelligent systems, but isn't the only angle one may consider like to advance AI forward. There are multiple other like goals. One could be computation efficiency, like in environments where computation is expensive, time efficiency in time restricted environments, energy efficiency in biological systems, for example. As but the other are that this information efficiency measure could be a proxy of multiple of these concerns too. So now the authors also include an implementation, like or like yeah, have an example of how to implement this, and for that they develop a data set called abstract and reasoning corpus. This is available in GitHub in this page. And the ARC can be seen as a general artificial intelligence benchmark, as a program synthesis benchmark, sorry, or as a psychometric intelligence test. It is targeted at both humans and artificial intelligence systems. And well, it stay close to what is this? Sorry. What it stay close in format to psychometric intelligence test, focus on measuring developer aware generalization rather than a specific skill, and it explicitly described like the complete set of priors it assumes and enable a fair general intelligence comparison between humans and machines by only requiring priors close to innate human prior knowledge. Let's this is how it looks in the GitHub page of the author. Like it is separated between data of training and evaluation, and it has a hidden set of of tasks that they use to create competences in no contests in Kaggle. This is how they look. They develop like a task demonstrator stuff, and it's most like geometrical assembly problems and tasks. Like you can here see like they give you two pieces and you have to turn them all to the same side with the largest one prevailing, and that's one task, and they have 400 different tasks, right? One of those is they give you an empty space and tells the system to create a symmetrical shape on an empty space according to the pattern. Another task is to count the element that repeats most times, and things like that, like data cleaning. Like you have these green entities, and then you got to remove the noise. And those are kind of the tasks that like they consider. Um, and how to implement this? Like, they suggest that a hypothetical ARC solver may take the form of a program synthesis engine that transforms input grids into output grids. Like first, the developer has to develop a domain-specific language capable of expressing all possible solutions programs for any ARC task. Um, it will require hard coding the core knowledge priors um, in a sufficiently abstract and combinable program form to serve as basis um, for a kind of human-like reasoning. And well, I find that personally kind of interesting from the point of view of our field of study. What could be those priors that we'll have to consider in an hydrological atmospheric focused like implementation of this framework? Things to consider, and that's it. That's what I have prepared for today.
Thank you, Andres. Does anybody has a question for Andres?
Looks like Joseph has a question.
Yeah, thanks for the presentation. I I didn't realize we were going to be talking about algorithmic complexity today, but I was randomly reading a paper about it last night. And what I got from the paper was that no one can really, I mean, it's an old paper, so things could have changed. I think it was from like the 80s, but I think they mentioned that no one really ever measures that algorithmic entropy. But I'm just wondering if that's changed since then. Like, do they ever try to measure that entropy quantity in this paper?
Hi, Joseph. I'm not sure. I'm not sure. They mentioned other methods have been used to evaluate intelligence in a fair fashion. But what we these methods have in common is like they develop their own data sets to like to to prove their point. But I'm not sure if that entropy measuring is being applied. To be honest, I don't know.
If I could take a shot at that, Andre.
Please.
Um, so the important thing to understand about this paper is that it's a theoretical presentation. It's based on the assumption that you can measure all of these quantities, and they've all been theoretically defined. Second is that it's not algorithmic entropy, it's algorithmic complexity that we're dealing with. And complexity is measured in terms of the number of yes/no questions, or the shortest length of the length of the shortest binary string, which, when processed by a program, which expresses a program which, when processed by a universal Turing machine, will generate the correct answer. So this is different from the notion of surprise or entropy, which is Shannon entropy, except that it is measured in the same units of bits. Does that make sense?
Yeah, actually, the paper I was reading last night was kind of relating both these quantities, and surprisingly, they actually kind of have a lot of the same properties. So if you look at the mutual information of both, I mean, it's might be, I can't really remember the terminology, but like if you look at the algorithmic complexities notion of mutual information, it still almost satisfies the information non-increase when you apply it to like a deterministic function. And yeah, there's a bunch of other properties that it still satisfies. So yeah, they are seemingly closely related, but yeah, different names.
Well, they're related through the notion of surprise, when surprise is expressed as the number of yes/no questions you have to ask. In other words, the number of yes/no operations. Okay, so that's, I mean, to understand all of this, what helped me a lot was finally basically understanding that the universal common ground is only achieved when you think of it in terms of yes/no questions or 0-1 specifications of zeros and ones. And so you can only measure surprise in terms of the negative log probability of some event. What that tells you is how many, when you measure that in bits, it tells you how many yes/no questions you have to ask in order to resolve the uncertainty. So you completely remove the uncertainty associated with what the value is, what state the system is. And here what we're talking about is how many yes/no questions you have to ask, 0-1, and then processed, expressed as a program, which is then processed through universal Turing machine in order to perfectly resolve the uncertainty. So they're related, but surprise takes this statistical perspective. It's assuming that you're starting with some uncertainty, which is described by some probability distribution. Whereas algorithmic information theory says, starting from some point, how many yes/no questions do I have to ask in order to answer that question?
Yeah, I think that's the key. I think like the Shannon entropy is about distributions, and this is about objects. And I think they mentioned in the paper that the algorithm, the expectation of Shannon entropy is the same or very, very similar to algorithmic complexity. But yeah, it's very interesting.
When you're taking expectation, you're saying on average, how many questions do I have to answer, as opposed to specifically in this particular situation, how many questions?
Yeah.
We have a question in the chat from Dan. He asked, can the relative algorithmic complexity here be interpreted as the encoding decoding program, or it is something more general?
Andrés?
Yeah, well, from my understanding, is like the encoding and decoding program. The responsible of this is a space and space non-related to the relative algorithmic complexity. Like the relative algorithmic complexity calculation already receives inputs in binary strings from our situation and response space. That's more or less what I got regarding that topic.
Yeah, I think I have a slightly different understanding or interpretation, Andrés, and that is when you say talking about relative complexity, you're saying given some information, how much remaining information do I need to provide? So that information can be given in many, many forms. It can be given in the form of data, but it can also be given in the form of a algorithm or a Turing machine, which has some prior knowledge about how to process things, right? So it's always conditional on the alphabet, the language, the processing ability you already have. And the way I like to think about this is, if I had to start and do some calculations without a computer, it would be incredibly difficult. It would be very, very complex. The moment you give me the computer, which is a universal Turing machine, has the ability to do all this processing for me, it makes the complexity of the task much reduced, because I'm presuming that complexity, which is already built in, and that's given. That's the part that's already given to me, so it makes my job easier. You could even say that the whole trajectory of human civilization is trying to reduce conditional complexity by pre-solving problems. And so now you can, so if you had to start from scratch, like if you were thrown back into the Stone Age, you wouldn't have all of this ability. And going to the moon would be much more complex than it is today, as an example. Does that make sense, Dan?
Can you hear me?
Yes.
Okay. Yeah. I guess I was kind of thinking more practically about the directions, because we do need two, I guess two different programs, right? One to encode the original signal, and one to take the encoded signal and return it. And I would just wondered if that was reversible in this in that factor there.
In which factor?
Sorry, in that H of S1 given S2. If you could call anything, or either one S1 or S2, like the encoded versus the initial or raw signal.
Sure, you could, but then the conditional complexity would be different, right?
Yes.
Like there may be no information in S1 about S2, for example. But there could be a lot of information in S2 about S1.
That encoding and decoding part remember me of a discussion we had early on this group on how to better encode like the fundamental laws that we want our model to learn and the underlying truths. And it seems here like, as this is like a geometrical shape playing stuff so far, well, it's more or less simple to encode, but still I feel like this is kind of far from applicable. Like there is so many things to think through in, like, for doing hydrology, for example.
Well, nobody's yet given a mechanism for actually calculating algorithmic complexity in a universal way. And part of the reason for that, I think, is because it's always relative complexity, and you always have to presume something in order to calculate the complexity. So if you presume that your distribution is Gaussian, then you can calculate the entropy or the surprises associated with the observations, the random values. But if you don't know that it's Gaussian, then the conditional complexity is much larger, because you have to first determine that it's Gaussian. So S2 could be the information that the distribution is Gaussian. Dan, I think Stephen made some of these assumptions in his compression paper. And then
Yes, hydrozip.
Yeah, hydrozip. So the moment you assume that you know what that distribution is, you make the problem a lot easier. And then you just calculate the conditional complexity, which is the remaining amount of information you have to provide in order to resolve the problem. But it becomes even more interesting and complicated, because you have to assume that you have a computational system. So how much information went into providing that computational system to start with, right? If you have to go and collect the data to answer the question, then you have to also include the amount of work that you have to do in order to collect the data. So everything is relative to what you can assume as given.
yes, the author also mentioned like the priors, uh, like trying to, I don't know, to account for that. And well, this prior like geometry, I don't know, persistence of the objects are not universal, right? Like in atmospheric science, two, I don't know, air pollutants can be in the same place theoretically, or yeah, things like that. Like it makes me think a lot. Yeah.
I like the framing because it gives you a theoretical way to think about the whole problem. But the question that Joseph asked earlier is very valid. And towards the end of the paper, he basically says, now we need to come up with approximate ways to do these calculations. He doesn't tell us how to actually do them. It looks like Isabella has a question.
Hello, thank you so much for the presentation, Andres. So I would like to discuss something about the priors. So like according to what Andres presented, so intelligence of a system is the measure of how it's like his skills acquisitions like in an efficient way and over like different stacks, having in mind the prior of the experience and the generalization difficulties. So I have like something, I'm just wondering like how we know or how we can know if a system is intelligent if those priors of experience are not being like memorized. Like, yes, I don't know how we can understand like the priors and the experience without memorizing them. Like the system is not just memorizing them, most like generalize them. I don't know if I was clear with the question.
Yeah, I think I understood. And the priors are hard coded knowledge in the systems. Like it is something that like a base level for the systems, yeah, that you aim to compare. That comes to what Professor just said of if you account that you start from like from the Stone Age, like well, you have to account for computing power. I mean, for multiple things. So these priors are like the base level for for the systems to compare. So they are hard coded and known because are user defined.
Thank you.
So in your language, yes, the priors are what you've memorized. Whether you understand them or not is a different issue. Hernan.
Yeah, great presentation, Andres. This is a reflection, perhaps for all of us. It seems like the paper, it's written in a way that it it tries to explain intelligence from the top down. In other words, the truth from assuming that we can know the truth, how much can our systems explain the nature based on that truth? And that practically it probably is impossible to do, but it's theoretical. One other way to do it could be, and this is based on a question that I asked ChatGPT, what's intelligence? And one of the answers that it came with is the theory of successful intelligence, which was proposed by Robert Sternberg, that emphasizes that the ability to achieve success in life is by adapting to, shaping, and selecting the environment that matches one's strengths and weaknesses, which means that now we're not so ambitious in having to know the truth, but we know what we can do with what we have. In other words, we create models, for example, hydrologic model, that we can't, at the same time that we create a model, we can tell how much the model can tell us about something in a way. Or we can say that we created a model that can, and we can select the environment for that model. However, that includes limited knowledge about the world, and that would be intelligence only of a particular length of history or a particular environment, or but it would be a more complete knowledge. And we probably now we could apply that theory to for example, if you think of the minimum description length based on the history of the data that we have, you can probably estimate some statistics, and then we can be confident that we can estimate the stream flow with this certain uncertainty. And then theoretically, our model could work for kind of the same environment and history. But now, that would probably be a way to localize the definition of intelligence, and make it more practical. I don't know what you guys think about it, but my perception is that this is overly ambitious.
Yeah, I think you're right. The author kind of acknowledges that too, and says that it makes sense to measure intelligence only in a scope of applications, right? So, like, yeah, the intelligence is the average of a property over task belonging to this scope. Like,
The scope.
so yeah, like to achieve something like universal intelligence or to measure intelligence on different scopes, like, makes no sense, according to.
I think the part that you didn't mention, Hernan, is that there's a big component of generalization ability here. So the whole point of his development over here is, given some training and some curriculum and some prior knowledge, you're measuring intelligence in terms of the ability to then take what you've learned by doing one task and apply it to other tasks, of course, within a scope, within a range of scope, right? So if you've only trained in hydrology, you might be able to apply that intelligence within the realm of hydrology. But if you can now do streamflow prediction, but now you use that ability to predict the stock market, that's a generalization ability. Okay. And now you use it in another context, but it's still only doing time series prediction, right? And now if you can take what you've learned about time series prediction and use it to predict something else, which is not time series, like maybe prediction in space, right? Then that's another generalization, and so on. So the whole point over here is that if you can just regurgitate what you've learned, they're not calling that intelligence, or they're calling intelligence. And in the context of machine learning, which is actually one of the places where people have discussed this a lot, is you're assuming certain priors and so on, but then can that program that you solved solve other problems, right? So when you go to DeepMind, they started with AlphaGo, and then they developed a more general one where it could you didn't give it the rules of the game, and it learned the rules of the game by playing the game itself, and then it learned by playing a few games that it could play other games. And so that's sort of the direction that they're trying to go with this. And what he's trying to do over here is give a way to actually measure whether what you're doing is actually answering this question of, is it developing intelligence, or is it more intelligent or less intelligent? Because prior to this, you had something like Robert Sternberg or whatever, I don't know the guy, but just general comments. They say this is intelligence, but you can't measure it, right? You can't quantify it in some sense. Looks like Isabella had her hand up.
No, that's okay. Thank you.
You'd say a little bit more about Andres, I think, because the example that he gives of the what do they call it, the problems at the end. What do you call ARC, the ARC challenge? Is that what he calls it?
Abstract and reasoning corpus.
There you go. Yeah.
Data set.
Yeah, I think that was very helpful to me in understanding this paper, is that he's giving examples of problems that you're setting out to solve, which require a certain kind of prior knowledge or understanding. And he was trying to categorize what that prior knowledge should be in order to solve these problems. But what you didn't say, I think, Andres, was that the success rate of any existing AI program which has been tested on this ARC data set is very, very low. I think like 10 or 15% or something, if I remember right.
Well, I didn't knew that but it's good to know. And the key thing about this data set is that there is no two equal tasks. Like, you gotta create this skill program that is able to identify like the task and handle it. So yeah, it's not surprising to me that's so low performance.
So they give you these examples. So you got the thing on the left and you're given the answer, and you got this one on the right and you're given these answer. So you're given 3 examples here with the answers, and you got a reason, and you got to figure out what the rule is. And
Yeah,
then you got to answer the last one, and you got to fill it out and give the answer correctly, right?
exactly.
So this is
Yeah.
the kind of thing we have in human intelligence tests, for example, but this is much more interesting than the ones that we're given, right?
Yes. Yeah, and there are multiple like different. Those are just only ones, but there are like merge objects when they touch, and then count number of things like that. Like, very diverse. And they keep some of these tasks like hidden from public for those kind of contests
Right.
for people not to hard code a solution.
This sort of reminds me of the competition that was made, the programming competition, right? Where people are given the rules of the game, and then they're given or they're given the problem, and they're given some examples with the answer, and then the programmers had to write computer programs to solve that problem. And then they developed a LSTM based problem solving thing, a sequence to sequence thing, where so the reason it's sequence to sequence is you give it this verbal description of the problem with the example, and that's the sequence in. And then it has to learn to generate the computer program, which will give the correct answer, right? So it's a sequence prediction problem. You got to take the data which is given to you, like this examples, and then you have to extract the rules, embody it as a program, encode it essentially, and it has to solve. And they were able to develop, after training it on past history, they were able to develop a program which performed above the median level of performance. So it was better than 50% of all the expert programmers who were participating in that competition. But that sort of reminds me of this example of the ARC type of test. You know, you learn from examples, and then you have to learn, and then you have to develop a program, and then it has to be able to solve any general, any problem. Yeah.
Thank you, Andres. I think this was a great presentation, and I like the way of how intelligence is seen here. It's more like a more human-like, resourceful idea of intelligence rather than knowing how to do things. It's learning how um, use whatever you have to solve many different problems. So I think it's getting more to human-like idea of intelligence. I don't know if creativity is gonna be the next step into human-like systems.
The other part of this that I liked is that it puts it in context, right? So we live in cities, and we like to think of ourselves as more intelligent than people who grew up in the Amazon, in the forest, right? And You take the people out of the Amazon, you put them in a city, and you say, look, they can't survive in the city, right? But actually, you take me and you put me in the forest, probably I will not survive. So who's more intelligent? It's a misquestion, right? It's a misstated question. It has to be relative to your experience and training and the context in which you're put. But you could put a bunch of people in a particular context and say, I've got exactly the same training, etc. Then you could say one person or one machine is more intelligent than another if it's able to solve a whole wide variety of problems faster and you know and with less effort, presumably.
Right. I think that is what is measured with the efficiency on how you solve things, right?
Your words make me remember, Hoshi, in the Petros Dominguez book. He says that intelligence is the mix of knowledge and skills, and knowledge is statistical, and skills are procedures, which means that you can always use your prior knowledge to create analogies to a new world or to a new situation and adapt. But then the access to the dictionary is your prior knowledge. Probably the way you create analogies is the intelligence, and you adapt. That's the human component that Lila was mentioning. That's what humans would probably do. I don't know what machines would do to adapt or learn in new environments.
By the way, I should mention that all of this presumes the existence of a universal Turing machine, right? And people argue that modern computers are universal Turing machines, right? So in order to measure all of this stuff, and so that, what does that Turing machine mean? What can it actually compute? It says all possible computations, but we have to define what all those possible computations are. And that has to be specified in the dictionary that the universal Turing machine has access to. So if you look at a machine learning program, it only has access to linear affine transformations. Let's say, assume rectified linear units, so multiplication, addition, rectified linear unit operations, which are basically yes/no questions, right? And maybe softmax operations and averaging operations and so on. And so it's got a limited dictionary. Based on that limited dictionary, it has to answer the question. Yeah. But if you give it the ability to use logs or some other activation function, you give it a bigger dictionary, right? So you can potentially change the conditional complexity of the task based on whether you gave it the priors that it needs to solve the problem.
Now the other question is, and this is related to Lila's comment too, can machines develop creativity? Is creativity a measure of intelligence, or intelligence is just the accessibility of the dictionary to create the adaptability necessary to answer a question in a new world? Can machines be creative in that sense? In other words, can they create surprise that hasn't been learned before? That's I don't know. That interests me.
I'm going to look for a link, but Andres, you want to take that one while I look for this link?
Sorry, Professor, say again. Are you sending a link?
I'm going to look for a link, but maybe you could take a shot at the discussion with Hernan.
Yeah.
Look for it, yeah.
Yes. Well, regarding Leila's and Hernan comment about creativity, well, I bet 99% of people alive agree that these drawing AIs are creative and so on. But well, now they are trained on something. But what if those were trained on nothing? Then they could do random randomness, and that can be argued to be creative, but if it has not like static criteria, then it's just random stuff. So that's another thing that will be very hard to measure.
So it's interesting your question, Hernan, because there's an article, I'm looking for the article too, but this paper has recently come out, A Theory for Emergence of Complex Skills in Language Models, where these authors use a very interesting mathematical development using graph theory to argue that modern large language models are not stochastic parrots. In other words, that there is an emergence that happens where the language model develops the ability to do something which they argue is closer to understanding, like the way humans understand something, because of a certain amount of size and complexity leads to an emergence. And that emergence could not be predicted from the individual components. So even though it was trained, even though the large language model is only trained to do word prediction, conditional word prediction, it's actually able to solve more complex tasks than just word prediction. And so people are arguing for this as an outcome of by passing over a level of threshold of complexity. And they've got some theoretical arguments here. And these arguments apparently have convinced or are well received by people like Geoffrey Hinton and others, as thinking, yes, this sort of makes sense. It convinced them that they're not just statistical engines, that something more interesting is happening. Let me see if I can find the popular article. That one's easier to read.
Ocean, I put the link in the file of the title that you put in the chat. Is that the article you were looking for?
Is this the popular article? This is the paper, right? That you just put in?
Right.
Okay, yeah, let me look for the actual sorry, new tab.
While Hoshin's looking for that, I had one other question about this kind of Kolmogorov versus Shannon entropy stuff. So I'm wondering in hydrology, which one's actually more useful? Because in hydrology, we never really deal with probability distributions necessarily. Like we can approximate them, obviously, but those approximations aren't that good anyway. So is like the shortest program kind of more related to what we are searching for in hydrology versus probability distributions? Does anyone have any thoughts about that?
Could you repeat that question again? Sorry.
Yeah, I'm just wondering in hydrology, if it were actually possible to kind of measure this Kolmogorov complexity, would it be more useful to us than the Shannon entropy stuff? Because in hydrology, we never actually deal with kind of probability distributions. We more want kind of this universal E equals MC squared equation that gives us back every hydrological process. So which one's actually more related to hydrology if we were able to measure both kind of exactly?
So the Shannon entropy thing you can think of as being closely related to the idea of characterizing the correct probability distribution of some random set of random samples. It's the same as maximum likelihood. You maximize the likelihood that those samples could have been generated by some probability distribution. It's the same as minimizing the Kullback-Leibler divergence between your model and the data, right? Does that make sense?
Yeah. No, I know, but
Okay.
I'm wondering.
So what Stephen and Ben have done is they've written a paper which explains this nicely, where they're saying that the problem with that approach is that you need a hypothesis, and then you just have form a hypothesis and you got to test it. You got to form a hypothesis, you got to test it, and so on. And what it doesn't actually enable you to do is to measure how good your hypothesis is relative to the problem that you're trying to solve. So there seems to be a reasonable amount of evidence which says that a better performed hypothesis, one which is less Kolmogorov complexity, if it can explain the data equally well, will generalize better. In other words, you can trust it more when you make predictions. Does that make sense? So
Yeah.
The simplest way for me to answer, to compare against the data, is to have a model which is just a memorization of the data. So if I just memorize the data and I say that's my model, then I cannot trust it. I have very little trust in it in making predictions into the future or in some other context. So what I'm trying to do is extract some underlying principles. And the argument is that the model, which is the least complex explanation of the data, which explains it equally well, is going to be the one that is going to better generalize when I need to use it in some new context. So it's relevant in that sense, but it's not specific to hydrology. It's a general argument.
I see. Yeah.
And so that's why we use the principle of parsimony, right? So things like a key information criterion, Bayes information criterion, Kasha, KIC, BAC, AIC, these are like approximate ways to help you control the complexity of your model by adding these penalty terms, which are essentially saying, what's the description length of the model? And I add that to the description length of the residuals, and I minimize the two, which is what Ben and Stephen talked about in their paper also. Another way to understand that, Joseph, I guess intuitively, is if I give you some data and you fit a polynomial curve to that data, you can fit a very high order polynomial that'll pass very close to those points. But now if I want to predict outside of the range of the data, I would have very low confidence in it predicting outside of the range of the data. Whereas if I just fit a straight line through that data, I'm going to have, because it's extracted a trend. And so if a low order polynomial, first, second, and third order polynomial, is likely to give me a better explanation of what's going to happen when I predict out of range than a very high order polynomial that fits the data perfectly. So I put in the link, Leela, maybe you could bring that one up.
Yes. I think Andres, you had a.
Or Andres could bring it up.
Yeah.
Yeah, so this is that article you guys might find interesting. It's in a slightly more understandable form. They're trying to address this question: is do models actually understand what they're saying? And really the question to me is, what do you mean by understand? Right? You could argue that a machine learning model, even if it's not interpretable, if it predicts if it makes predictions on new data better, then a physically based model, you could argue that the machine learning model understands the system better in the sense that it makes predictions, but it doesn't understand the system in the sense of it can explain to me why those predictions make sense.
Well, I would argue there are two different understandings.
Right. Yeah.
But probably converge to the same solutions, the non-unicity of solutions to the same problem.
Right. So here they're actually saying that it has something to do with this emergence, right? That somehow, like if you look at, if I give you a bunch of data and I put it on an XY plot, and you just look at the data, and you come up to me and you say, okay, I'm going to fit a straight line on it, then you could say, yeah, I've understood the data in a sense that I'm saying that there's a trend there. I've compressed the data down to some understanding, right? And I can use that to predict out of range or to interpolate or to do something. Anyway, you might enjoy this. This article came out fairly recently. There's the thing about creativity. Yeah. So I guess the question then is not just understanding what does it mean to be creative, to come up with new examples.
So it somehow means that it goes beyond the training. In some way, it learned to not only learn from the past, but to create in some way, I don't know how, which could probably be beneficial to some models that we want to resolve the climate change, for example, the non-stationaries and stuff that is not necessarily present in this historical data. Yeah, we will have to see how much the large language models can help us understand non-stationaries. Stuff like Praveen has mentioned in the past. Can machine learning model help us understand things that we don't have in the past? We haven't recorded yet those events. So that's a good hope, I guess.
So I would argue when you combine things in some novel way, that's kind of a creativity process, right? You combine things in ways that nobody has done before. So if somebody does something like that, we say, oh, you're very creative, right? And the other is your ability to answer counterfactual questions, which means to put yourself in a different situation from a situation you've already been in, and use the knowledge, use the information you gained from the situation you've already experienced to answer questions about some situation you have not yet experienced, which is kind of like extrapolation.
What comes to mind is something, now we're talking about creativity, something that didn't become clear to me until recently, a few years ago, was that people always talk about intuition, right? And I always thought that some people are highly intuitive, others are not. And it's really hard to explain what is intuition. But I think in terms of Micah, I mean, I think that really drives research, decision making. Then 3 years ago, I was at Broome Woods. That's a UCLA conference facility at Lake Arrowhead here in California. And for UCLA graduates, they opened that up 10 weeks of the during the year in the summertime. You can go visit for the week. Families are there and kids are entertained. It's a wonderful, lectures are given. So anyway, so I ended up talking to a police psychiatrist. So the lady has been working with LAPD, like hiring which new police officers, or if a bad event happens that they need to talk to someone. Anyway, so I was talking about all this, and suddenly she said, Jasper, intuition there's actually a good explanation for that, and that is that those are patterns that you've learned from a young age on. And when those patterns where certain events line up, that is what gives you that intuitive feeling of something is going to happen now, something. So that is, in some sense, intelligence, right? That some people don't see these patterns at all. But anyway, made me realize, conclude that in essence, intuition is pattern recognition. Events that seem unrelated to a lot of other people, that you actually from childhood or something, that you're able to see that, and you suddenly see, hey, it's probably heading in that direction. So related to these, I just read this piece that Hoshin sent in that paper. I mean, I read through that. It's very interesting that those large language models actually can do much more than predict the next word, that there is a deeper ability that the network can actually do much more than that, meaning that in terms of brain development with children, that's why they always say, when I was at Los Alamos, one of the take-home messages was that when I was at the Santa Fe Institute was, take your child to as many countries in the world within the first 3-4 years, because being exposed to all those different languages is really going to enhance learning. It activates parts of the brain. And so it's completely consistent now with what you see here, that learning of languages actually creates much deeper skills, much deeper ability. I just thought I was going to add this to the mix. And my question was also, can we see a watershed as an algorithm? Okay. That was my only question. Okay.
If I could add to what you're saying, Jasper, it's not just languages, Chinese, English, Dutch, French, Spanish. Math is a language, hydrology is a language, atmospheric science is a language, ecology is a language, music is a language, physics is a language, chemistry is a language. It's, of course, they may be conditional on English as a language, right? Or something like that. But I completely agree with what you were saying earlier about learn as many languages as possible. If you go back in time, people were what they call Renaissance people, a lot of our famous scientists, in that they developed background skills in many, many different areas.
Mm-hmm.
And so I think they match this definition of intelligence that Andrés was presenting over here in a nice way, because their creativity and abilities was based on a much broader base of language skills, which allowed them to think thoughts that you couldn't think if you only had a very limited language.
So, but is it possible though that if we have a watershed, we have a discharge time series, we discretize that discharge series in a state space or so, where we can assign a 0, 1, 2, 3, or whatever what you want to use to a time series. So now you get a time series of a 0 or 1, which describes the event, high, low discharge, and then also the moisture content of the watershed. But imagine that we have a time series. Can we then compute the algorithmic complexity of the watershed?
Sure.
Okay, but that really relies on you being able to look at the time series and divide that up in a state space or so.
Yes. Yes. Okay. I would argue that a watershed is a machine.
Yeah.
Okay. It's a computational machine in the sense that it does transformations.
Yeah.
So there's this whole thing in physics about the universal constructor now, as opposed to the universal computer, right? It would be that the thing that allows you to make anything that can be made, constrained by the laws of physics. This is the work of Chiara Marletto and that we read, David Deutsch, and so on, right? But you put your finger on it. You have to define it to a particular resolution, right? A particular state space resolution. Except I think there's one thing which is missing from the Kolmogorov complexity description, and I've been thinking about this a lot recently, which is he only talks about description, but it takes work to create a description. And it takes work to do the computations.
Mm-hmm.
So I had this a little bit of a discussion with Steve. I think Dan was party to it in the early days. I think that more fundamental than description length is actually work done. The amount of energy and the number of operations you have to perform in order to go from A to B. So if the number of operations to go from A to B is very small, then you would say that's a very simple system.
Mm-hmm.
But if the number of operations you have to go from A to B is very large, then you have a more complex system. And if the operations are based on 0-1 binary copy, flip and copy operations, I don't know if that's how the universe is constructed, but if you assume it is, then in principle, you can add up the number of copy and flip operations that you need to perform.
And that's interesting because so you can think of if you build a car, you can go from A to B really easily, right? But it took a lot of work to build that car.
Mm-hmm.
So
the work done to build that car is reducing the conditional complexity
yeah,
of the task. Yeah, exactly.
yeah. But so have people published on this in hydrology where they compute the complexity then of just the raw signal and then do that with their model and then look at the difference of the two?
That's Dan, you can talk about that. Yeah.
Yeah, so I think part of Stephen's work was doing that. And I think what Hoshin just said about the actual quantization, I think that's where a lot of the problem is. And this is what has been haunting me for the last while, is computing that complexity, or I guess computing the entropy of the signal, and what is it sensitive to? And yeah, it's very, very sensitive to how you define the state space. Yeah.
So if you, just an idea, probably already done this. If you use a very high resolution deterministic model where you print out a lot of the states, right? Then for the most, at the highest resolution, you can compute the complexity, right? And now you're going to average in space and time, for instance, and see what that does to your estimates of complexity. I mean, that's why I would think to get some idea of some of the things you're talking about. Maybe that's an approach. And yes, this is all simulated data, but still.
So do you mean like the size of the state space, or like the quantization levels, like the
yeah, both essentially.
So
yeah.
I'm sorry, go ahead.
No, go ahead. Yeah.
I was going to say that's something I've been exploring, like changing the bit rate, basically changing the state space size. And then I got into like signal processing theory, because even if you get up to say 8 bits with this runoff data, you end up with a lot of empty bins. And so then it's an idea, like basically we have a range and we are just dividing it up, finding strategies to divide it up, and trying to avoid empty bins, because empty bins we can't compute, and then we have to add information, right?
So either you have to fill in the bins or you have to assume some functional form, like a distributional form or something. And so as Dan just said, then you add information, then everything becomes conditional on whether the information you added is correct or not. Yeah.
It sounds like as a fractal, right? What's the length of the coastline? Is that if you slice the hydrograph in high and low, and then you slice it in more and more steps, right? What happens to that complexity? Do you approach, I assume you approach a certain constant, or do you continue to increase complexity when you go finer, finer, finer?
Yeah, think of the flood forecasting problem. If you tell me that 100 meter cube per second is my flood threshold, then you just ask the question, is it above or below? One question, 1 bit, right? I have to reduce it to 1 bit. I only need 1 bit of information. But if you want me to predict it to within plus or minus 1 cubic meter per second, the actual magnitude, now I've told you the resolution, Now it tells you how many questions you have to ask, right? And then if you want to do it to 0.1 meter cube per second, then you have to ask more questions and so on and so forth. So it's always relative to the answer you're seeking. Yeah.
But I can imagine though that if you, at one point you keep slicing your state space, that you approach a constant value for your complexity, or does that continue to?
No, information keeps increasing at a logarithmic rate. So
The complexity, the algorithmic complexity keeps increasing.
Algorithmic complexity is related to the number of bits, 0, 1 bits that you need in order to describe your system. Okay. So let's say that you, and we know that if your probabilities are uniform, which is the maximum entropy, then entropy increases as log of the number of states, log of n.
I have the reason that there's something not intuitive about this, because I would think that once you approach the critical scale that determines the discharge, that your predictions or your understanding of the system doesn't improve by going at an even lower or higher resolution.
But that's because your understanding is relative to your ability to solve problems. If I tell you it's 20 meter cube per second versus 20.01 meter cube per second, that's sort of irrelevant, right? That is not useful to answering the question.
But does that drive the algorithmic complexity of discharge?
Absolutely.
That difference.
Yeah.
And that is in the resolution so that's in the binning when you define a probability distribution. That's where the decision is.
Yep. If you say I've got 10 bins, right? Then the maximum amount of information you have to provide is log of 10, log to the base 2 of 10. But if you say, no, I need it down to a resolution of 100th, log to the base 2 of 100. And if you say you want it down to a resolution of 6 decimal points, then it's log to the base 2 of that. Yeah.
So that's very unsatisfying in some sense.
Welcome to my world.
Yeah.
But I don't know, to me, from a decision point of view, it's extremely satisfying, right? Because you're basically saying, I don't need to provide an infinite amount of information. I only need to provide as much information as necessary to make my decision.
Yeah. But then I assume that what Keith Bevan calls limits of acceptability, those are going to be huge bin sizes, of course, then, but
Right.
I assume that a prediction of discharge that is 20.001, whereas reality is 20, that I would say that something between 19 and 21 is already pretty okay. But
sure. I think Stephen proposed in that case, well, he uses the log transform because it relates fairly closely to measurement error, because streamflow measurement error is huge. So
Fantastic, yeah. But I mean, the limits to acceptability notion makes sense in the sense that what you're saying is, as long as I have this precision, I'm satisfied, right? And with the heteroscedastic error, we have to tell you what's the form of the heteroscedasticity. So you're saying, what's the variance I'm willing to accept at low stream flows and high stream flows and so on, right? But once we specify that, then we've completely specified how much information we need to provide.
Yeah, and I mean, we published that paper recently, and we actually did it in 2005, and we also talked about it earlier today. That estimate of measurement error for discharge data, you can derive that from the data directly. This is a concept that a lot of people These are non-parametric estimators. Nowadays, streamflow is measured at such a high temporal resolution that you only need the data. Because basically, how do you estimate measurement error, right? You do repeated measurements at the same time. With the temperature, if you measure 10 times in 1 second, then you can imagine that the background temperature is the same. You measure 10 times, you have a sample, n values, you determine the mean and the variance is the measurement error, right? Now, that same concept you can do with discharge, except that signal is changing over time. So what you do is you difference the signal. You difference once, you just take the time difference, right? You can do it 1 time, 2 times, 3 times. What you'll see is that stabilizes, and then that is what comes out is the measurement error. So we published that, but so related to that, if anyone is working on that, you can get that heteroscedastic relationship out of just differencing your data, and then so this is the field of non-parametric measurement error estimation. And some papers in the 80s and 90s that
Sure.
have done that.
With the caveat, Jasper, that it's based on some assumptions, right?
You know, yeah, but not necessarily mathematical. The assumption is that your underlying signal is relatively smooth, so that you don't have this type of, which is quite a reasonable assumption.
It is a reasonable assumption, yeah.
And that your measurement resolution is high relative to the temporal scale of variation, which is also reasonable.
That's right. You're assuming that your change in values from one time step to the next, that your measurement error is not large compared to that, the minimum change in values. Yeah. Yes, that is the paper, Dan. Yeah, so I think there are reasonable ways to get at this by analyzing the data, but in every case you have to make assumptions, which means you have to have information.
No, I mean, I've worked on this stuff, but I never realized that in terms of algorithmic complexity, that if you keep imposing a higher and higher resolution, discretizing finer, that algorithmic complexity continues to increase. That doesn't have a natural bound. So then the fundamental question is, where do you stop?
Planck's constant.
Yeah. I'll read some of Dan's work then. Good, thanks.
So one of the interesting things that came out of our workshop in Schneeferner House in Germany, which I didn't realize until we had that discussion, is that even the measurement of entropy is relative, right? It's relative to a uniform distribution. Okay, so everything is relative. There's no such thing as an absolute measurement of information. There's only relative measurement of information. Once we get comfortable with that, then it all makes sense.
Another question I have been fighting with is coming up with the quantization strategy that relates to the specific question, because every question we have will have a different, quantization that's.
I agree. You have to ask the decision maker what is the quantization that they're willing to accept, and that's what makes all of this subjective, right? You have to pre-specify that the limits to acceptability, whatever language Keith used, because everything depends on that. So every question has a unique answer. So I guess what you're really saying, Dan, is that you're struggling with it in the context of hydrological decision-making or problems. And we're going to have to specify that. If you want to do the compression challenge, for example, you're going to have to specify what that means. And we all have to agree as a community that that makes sense. And if you want to change it, then you have to be very clear that I'm going to change it. And I'm going to answer the question in this context, right? Because the answer is always going to be different. The problem with mean squared error as a metric, for example, is precisely that it makes a very strong assumption about what that quantization is, right? And it does it in such a way where it discounts low flows and it only counts high flows as a meaningful part of that metric, right? Yeah.
Yeah, I think that a lot of people don't realize that when you use a mean squared error, essentially you're telling the model that you want the model to predict the mean of the data. When so there's basically there's an inherent, you elicit a certain response from the model. So if you think about calibration, right? When you use the squared residual, you elicit the response from the model that it describes the mean, that the parameters will be adjusted so that you attempt to describe the mean. If you use an L1, you'll predict the median of the distribution. So oftentimes in calibration, we already elicit a response, but then the model is used for something else. And the point is, so the paper that I present also here is that the calibration, the loss function that you use should match the application of the model.
I just go a little beyond what you just said, Jasper. It's actually biased towards predicting the mean, the standard deviation, and the cross correlation, right? That's the mean squared error decomposition work that we published years ago.
Yeah. But the reason is that those other metrics come into play because we have an evolving distribution.
That's right.
From a purely forecasting perspective, an L2 will get you the mean of the distribution. The fact that we don't get the exact mean, right? We get a bias is because of model error, right? And we have an evolving distribution with time. And
actually, it's actually two parts. It's because you have a bias in the model error, but it's also because when you minimize mean squared error, there's a trade-off between getting the mean right, getting the standard deviation right, and getting the correlation right. If you look at the decomposition.
Yeah, bias.
When you minimize mean squared error is equal to delta mu squared plus delta sigma squared plus 2 sigma is sigma O times 1 minus rho, right? So it's going to minimize that sum.
Yeah.
And if it can minimize the variance easier than it can minimize the mean, it will do that, right? And it'll give you a bias.
But that bias, that happens because your model is imperfect and you have in a time series, you have a distribution that's evolving. So that mean is different for each time.
That's correct.
But if you had the perfect model, that shouldn't happen. So you get these additional terms, but basically they call it elicitability, that we should only use metrics that we can actually, so your loss function should match the goal of application of your model. That's a really important, and now oftentimes also in machine learning, people always use squared residual loss functions, and then they evaluate for something completely different. And particularly in the climate world, right? All these models have been trained for the mean, and then they're used in decision making for extreme events. Those are quantiles. So we should have done quantile training, or anyway.
Yeah, no, I completely agree. I mean, when people were calibrating rainfall runoff models before a few of us got involved and started saying, here, let's do it automatically. How did they calibrate? They calibrated in order to get the volume of the hydrograph right, the peak, and the time to peak, right? Then they would adjust their parameters to match these things up. And so they were doing essentially what you just said, Jasper. They were matching their training to their objectives, which was they wanted to make sure they approximately had the volume right, the peak prediction right, and the time to peak right, and they ignored other aspects of the hydrograph. And if all you want to do is classify floods and no floods, then you use a different loss function, right? So.
Yeah. But I think, am I correct that I'm quite familiar with this squared residual stuff, and then Jacobian, Hessian, gradient, and then training of networks and all. But if you use any other loss functions, an L1, for instance, then I guess that standard packages for large language models training and all that they all use L2 functions or not, squared residual function.
No.
You can use any objective function you want.
No. Large language models are based on minimizing the surprise of the word predictions.
Yeah. So, and based on the probability distribution, right? They have a large database, and then they assign probabilities for each word.
No. They empirically calculate the success and failure rate. Okay.
But isn't it? Yeah.
So you're familiar with logistic regression.
Yeah.
In logistic regression, your output is a probability. Does that make sense?
Yeah.
Okay. So what they do is, in a large language model, let's say you've got 10,000 words that you can select from. Okay. You predict the probability of every word. So
Yeah.
you output 10,000 probability values.
Yeah.
And then the correct word, you assign a correct probability of 1.
Yeah.
And let's say the probability I got was 0.4.
Yeah.
So now the error is 0.6.
Yeah.
And now you do this for lots of words, and then you adapt your parameters so that probability prediction is minimized.
Yeah.
So it's not a mean squared error. I mean, it could be, but it's not.
That was my question. What exactly that question? I suspect that it is a squared probability loss function, but I think that's
the log loss.
So yeah, it's a log loss. It's basically you're not predicting a value. You're predicting the probability of being correct.
Yeah,
and so that's like in binary classification, right? You predict, is it 0 or is it 1? Yeah.
So this is a scoring rule essentially.
Yes.
So it's an how do you call it, categorical forecast, right? Of which one word hits, you have m categories, and then you can even compute the Breer score in that one bin, and you want to minimize that.
That's exactly it. Yeah.
Yeah, but those are squared. Most of those are squared residual or squared probability, or so. Anyway, what I was wondering, can we generalize network training to using any other metric, KGE?
People do it all the time.
No, I think they do network evaluation, but do they actually train?
Yeah, our papers, when Yuan and I submitted 2 papers WR, they both use KGE as the training metric.
Okay. And that uses gradient-based?
Yeah.
Backpropagation?
Yeah, it's because modern machine learning things do automatic differentiation, so you don't have to worry about it.
Okay.
Yeah, you can change a cost function very easily. It's almost trivial now.
Okay. So what language do you use? Is this in Python? Is this in MATLAB? What?
Python, yeah.
Python.
Yeah, because all these packages now have automatic differentiation capability.
Because you're going to get a very different Hessian for the KG that you're going to get for a squared residuals loss function.
Correct. That's correct.
And a Jacobian. So, okay.
That's correct. And we
okay.
generally get better performance using KGE. I mean, that's sort of empirically people have found.
A better performance in terms of what?
In terms of consistency over prediction when you test it across a variety of range of behaviors of course, you also have to make sure that the data you provide is not biased for training. Yeah.
Now, I thought it was a really nice paper I read that you did with about machine learning, and then across the United States, that machine learning, at least to took from the paper led to completely different conclusions about the need to use a different model structure or one model structure for the entire US, that actually physics-based modeling can lead you in the wrong direction. I thought it was really interesting.
Are you talking about the snow paper?
Yeah.
Okay. Well, all we were really trying to do with that paper was show that there was more information in the data than had been extracted by the physics-based model.
Mm-hmm.
And that as a consequence, the physics-based model, which is SNO 17, had to be calibrated location by location. Whereas the LSTM-based model, you could calibrate a single model for the entire country. And so really, the model error led to you having to adjust the model place by place, whereas if you used a LSTM-based model, you could use a single model structure. And so in other words, the location was less important. All the information was encoded in the signal itself.
Well, that's a very powerful conclusion, I think.
Well, it's powerful if we can now go back and build a better version of SNO 17.
Yes. Yeah.
That would be the goal. I'm hoping that Yuan will eventually do that. Yeah.
This is an interesting conversation. I think and this is something that Isabella is doing in her PhD. The latitude and longitude and time encode a lot of information already of your system that is somehow redundant with the other physics-based variables, but it helps a lot informing the machine learning about some other variables like solar radiation, temperature, precipitation, runoff stuff. So somebody should do a
But I'd be a little bit cautious with latitude, longitude, Hernan, because the same latitude or the same longitude in a different part of the world will mean something different. Okay. It depends on how far you are away from the oceans. It depends on pattern and so on and so forth. So I prefer to use the meteorological variables themselves because they already encode that information about distance from the ocean.
I have seen different examples where they use the latitude and longitude and time because they need it, for example, for predicting earthquakes. That they need that, and then they kind of forget about the physics of that. But in itself, the X, Y, and Z and T explain a lot of the variability, and it's impressive.
Sure. Of one point relative to another, as long as you don't go too far away.
There might be some like unobserved confounders within the latitude and longitude information. That's interesting.
I tend to suspect so, but it's a good way of setting up a coordinate system, right? It gives you a reference frame.
And Hoshin, I was wondering if you've ever derived the closed form solution for the gradient in Hessian for KG. Has anyone tried that before?
Sure, a long time ago. I mean, it's part of what we use to argue for the fact that you would tend to underestimate the variability of the data if you use mean squared error, and we use that, to help redesign the metric.
KG. Oh, okay, so it's in the original KG paper.
Kind of implied, but I mean, it's not that difficult because you've got basically three terms: the mean, the variance, and the correlation. And each one of those terms depends on the individual simulated values. And so you can derive the sensitivity of the mean to the simulated value, and you multiply it by the sensitivity of the simulated value to the parameter. And so, I mean, I guess I didn't really publish it because it feels trivial. But does that make sense, Joseph?
I see. Yeah, it makes sense. Yeah. Is it locally consistent though? Like if you improve like one single prediction, KG always increases?
No, because KG, just like mean squared error, is based on the average properties, right?
But mean squared error would be locally consistent. So.
No, mean squared error is also based on the average properties, right? Because if you improve one data point, then you might decrease the performance on some other data point. Maybe I'm not understanding what you mean by
But
local.
it's just a sum, and they're kind of independent. You're adding up those errors independently.
You're adding up those errors independently, which means you don't care about the time order of the errors.
Yeah.
You're just looking at the statistical properties of the errors. In that sense, KG is exactly the same. Yeah.
Okay.
The difference is that every error actually depends on every other error. Because when you change the parameters of the model, you don't just change a single error, you change all the errors.
Yeah, of course.
Yeah.
Thanks.
Andres, I really appreciate you putting the energy into digging through that paper. I know that was a lot of work.
But it was an interesting paper. Like,
it's an interesting paper. I would highly recommend you go and listen to the interviews with him.
Yeah, there's a couple videos on YouTube, like people discussing about it. Like it's like a hot topic.
Right.
So,
And I found those interviews to be very interesting. Like there's one with Jan Kilcher, another one with I don't know if it was Joshua Bach. Anyway, there's several interviews there where you need to have read the paper to understand what they're talking about, but the interviews help you to understand the paper better because the paper gets very dry and and complicated as you're going through the math. It's like, what is he talking about? What's he talking about? Yeah, it's like learning a new language altogether, right? Yeah. So anyway, I found it interesting and useful to go and listen to some of those other interviews. He gets into, yeah. So are you planning to, did you just do the paper based on interest, or are you planning to actually, is this part of the work that you're
no, it's not part of my work. I was going through like the suggested articles, and just the title was catchy.
Yeah.
And yeah, just
Cool.
stick with it.
Yeah. I think this paper is going to take a few readings to dig into, because there's so much there actually to make sense of. Yeah. So, but it certainly changed the way it certainly informed the way I think about the world. So I thought it was great that way.
Yes.
All right, guys, what time is it? Ooh, 11.
So we actually have an open spot for the next session because Alison cannot make it.
Okay.
So there is an opportunity to continue this discussion or do something else.
3:20.
Dan has a question. How did my enthusiasm for the topic change? Well, like it gets me very curious about how to implement this in our field of study, like in atmospheric science. Like, how could we develop a system that doesn't aim to predict like a magnitude of rainfall, but like to understand the interaction between elements. And it feels very abstract for me at this point. Like i don't I don't see a clear way of doing it, but I look forward to reading more on this topic, but kind of applied, like kind of merge with yeah, with our applications, not this like so the geometric shapes and all this stuff.
Thanks.
No, thanks you all for this discussion.
So let me just share my screen, if you don't mind, Leela.
Yeah. Okay. So
if we don't find somebody else for next time, am I sharing something?
It says it's sharing, but we cannot see anything. It's just like, okay, now
Can
we
you see something?
Yes.
So here's my information theory definition of the goal of science. And I said it's to discover you can see this, right?
Yes, we are seeing
Okay.
the spot.
Yeah, to discover an interpretable minimal description length representation, including embedding that results in minimal surprise and generalizes well when tested against reality. So if you don't get anybody else to present next week, I'd be happy to try to defend this definition, and it might lead to some interesting discussion.
It sounds good. Yeah.
Because I've been thinking that there's actually three important components to information. The classical Shannon information, which is about surprise. There's complexity, which is what Andres talked about today, algorithmic information. But what I tried to bring up at the workshop was that this missing aspect of information, which is what I'm calling representational information. And because you can represent the information in many, many different ways, right? There's an infinite number of ways you can represent the same information. Even if you compress it down, you can still transform and rotate that representation. So I think that this thing about representational information, I think a way to talk about that, which I'm trying to work on now in my head, is that that's about interpretability and generalizability. So we choose a particular rotation or a particular transformation of that compressed representation, but we choose one which allows us to generalize, right? In other words, it has to be consistent with our language, the way we understand the world. Anyway, that might be an interesting discussion to have. So,
Professor, and is there any suggested reading for us to?
No, unfortunately, there's no suggested reading on that one. So okay. That would be me entirely speculating out in left field, based on the fact that everything that I see in machine learning about interpretability seems to be explainable AI, all seems to be about sensitivity analysis, right? How sensitive is this to that? But I don't think that that's fundamentally what explanation about it is about. Explanation to me is about being able to express something using the language that I already understand. Right? So there's nothing fundamentally more interpretable about a machine learning model or a physics-based model, except that physics-based model uses a particular language. And I went to school and spent years studying that language. And so when I explain it to you, I use the language of physics. And if Gray Nearing comes in and says, no, my machine learning model is equally interpretable, more interpretable, is because he can speak the language of machine learning. So to a machine learning person, it's interpretable in a different way than me. And the argument I want to make is that ultimately what matters is, can I generalize that into some other domain? Right? Can I use that understanding, and can I translate it to help me solve a different problem? Anyway, that's the kind of discussion that I'd like to have and get people to push back on, because I think it might help me to develop those ideas better. Yeah.
Awesome.
So I've been trying to answer the question: is it possible to measure the number of yes/no questions in a machine learning model, for example? Right? And I think maybe yes, but we have to talk about it. So, all right, I'll see you guys in 3 weeks.
Okay. Thank you so much, everyone. Thank
Goodbye,
you for the
everyone.
great presentation.
Right.
Bye-bye.
Thanks. I really appreciate the effort you put into that. Yep.
Thank you.
Bye.
No problem. Bye.
Bye-bye.